For example number 6, we're asked to show that there is some number x0 out there such that it satisfies this equation right here. Now, here's how we're going to do this. What we're going to do is we're going to let this guy right here be equal to a function, okay? So we're going to say, let's let f of x be equal to x to the 5th minus x, okay? And what we're going to do here is, if we take a look at this function, okay, at 0, I'm just picking 0. You don't have to pick 0. You could start somewhere else. I could start at 1 if I wanted to. Watch. I'll do it different than the book. I'll start at 1. Okay, here's 1. Well, f at 1 would be equal to 1 to the 5th minus 1, which is 0. So there it is. Okay. Now, more importantly, if I plug in, let's say, 2, here's 2, and I plug in 2, then f at 2 is equal to 2 to the 5th. You see why I picked 2, because it's a small number. This gives me 32 minus, whoops, not minus 1, minus 2. 32 minus 2, which is a height of 30. So here's 30 up here. Okay, and we know that the function is up here. Now, I have an interval. Okay, I've constructed an interval. My interval is from 1 to 2. Now that I've constructed my interval, I also notice that on my interval, f at 1 is less than f at 2. And the number that I want to show that's in between there, I want to show that the function, this function, is at some x value is equal to 3. Because, so this, I know is true because f at 1 is 0, which is less than 3, which is less than 30. So now I know that there's going to exist an x0 out there somewhere such that when I plug it in, I get the value 3 out. Okay? It guarantees that this is out there. The only thing that I haven't shown is that it's continuous. We need to show that f of x is continuous on the interval 1, the open interval 1 to 2. So that's not too hard to do. There's a couple approaches that we can look at. The most generic approach is to say this guy's a polynomial, and polynomials are always continuous. Okay, so that's one way of looking at it. Okay, another way, a better way of looking at it, in a way that you should begin to look at these things is, well, if it's differentiable on that interval, then it's also continuous. So let's take f prime of x, which is equal to 5x to the 4th plus 1. Oh, excuse me, minus 1. Okay? Now, this is defined from 1 to 2, meaning there aren't any problems with this. I can plug in any number between 1 and 2 into here, and I'll get a number out. So f prime exists for all x values that are on the interval 1, 2. Okay? So that's the way of looking at it. The other way that we could look at it, the final way that we could look at it, is with the actual limit definition. This is the best way. So the best way, okay, if you're going to be a math major or something like that, this is what you should be doing. The limits as x approaches x0, where x0 is inside the interval. The limits of f of x, well, now the limit f of x doesn't have any points of discontinuity, so this is, and that's what we're trying to show here, this is equal to, f of x is equal to x to the fifth minus x. Now, by using the limit laws, okay, this limit, okay, this is the limit as x approaches x naught of x 5 times minus the limit as x approaches x naught of x. And we've already proven that this guy is x naught, so this will be x naught to the fifth minus, we already know that this, using our limit laws, is just x naught. So this gives us x naught to the fifth minus x naught, which is equal to f evaluated at x naught. And since the limit is equal to the function, we know it's continuous. So we've shown continuity. And so now what we've proven is that this function, who knows what it looks like in between here, but we know that the height value of 3 and the function must intersect at some point, which tells us that there's some x naught value out there such that f of x naught is a height of 3. And so now we don't know where it is. This is an existence theorem. We show that something exists, okay? We don't know where it is, okay? We didn't claim to know where it was. We just showed that it is possible. It is out there.